Today's lesson is about graphing polynomials of degree 3 or higher. First, let's do a little review about polynomials. Polynomials are functions of the form given p of x equal to a constant times x to the power n plus another constant times x to the power 1 less, and all the way to a constant by itself. Any of those terms can be missing except for the first term, because the first term is telling you what the degree of the polynomial is. Now, so this one is telling you that we have all these constants are called coefficient, even the constant term constant. And we call the first one the leading coefficient, and the last one is called constant coefficient or constant term. Before we start graphing them, we sort of want to remind you how cool polynomials are. Polynomials are they're special because they actually approximate other functions and other curves. One cool example of that is spline curves, which is used in designing cars on AutoCAD. So first, we want to start with graphing by means of a parenting function. How do we do that? Before actually getting into that, let's give an example of a polynomial. Look at the polynomial r of x equal to negative 1/2 of x cubed plus 3x squared minus 6x plus 4. Oh, by the way, what is the leading coefficient here? Negative 1/2 is the leading coefficient. What is the constant term or constant coefficient? That's 4. And so that's the next question. Now, graphing this r of x is a kind of a hassle, and we have to do many steps. We have to find x-intercepts. We have to go through a bunch of steps. But look at this other function. P of x equal to negative 1/2 of factor x minus 2 to power 3, or cube of x minus 2. This one actually is more reasonable to graph. Why? Because it reminds you of parenting function y equal to x cubed. So this is actually a nice function. The part that I'm not telling you is that actually, if you expand this binomial, if you expand x minus 2 to power 3 by use of foiling, then multiplying the polynomials together, and you multiply it by the coefficient, you will get r of x equal to that. The reverse process is going to come out as an later lessons. So later we'll learn how to go from this function to this function. But right now, with your knowledge of multiplying polynomials, you should be able to go from this function to that function. So that is left as an exercise to you guys. Now, then, so if you expand them, you see that they are identical. Now, I know the parenting function. Let's try to graph p of x equal to this, which is going to be the same graph as that one. So, steps. First, we start with the parenting function, y equal to x to the third. See, I graphed it. I put in a couple of extra points. I put in the x-intercept, which is 0, 0. Put in extra couple of points. Those extra couple of points actually help you see how everything is changing as you use transformations to get new functions. So first step should be, I'm thinking, I want to do a shift to right or to left to get the parentheses x minus 2 cubed. How do we do that? First of all, how do I know this is only good for, not only, but it's mainly used for shifting to right or shifting to left. It cannot be used in all transformations. Some of them you can use, some of them you can't. So what I do is I look at my x-intercept to see if it's a shift to the right or shift to the left. X-intercept here is 0 and 0. That's an obvious one. If I said y equal to 0, I get x equal to 0. And then x-intercept here, if I said y equal to 0, I get x minus 2 equal to 0. That is x equal to 2. So the x-intercept here, 0, 0, moves to x-intercept here, 2 and 0. Oh, what kind of shift is that? That's 2 units to the right. Okay, so that's how I know. So the orange one, the x value is going to increase by 2. The purple one, x value is going to increase by 2. And then I can graph it again. It's just a shift 2 units to the right. Now, what else is left? I have to make that negative 1/2 multiplied by this function. And so let's do that. Negative sign multiplied by the entire factor, by entire rule of the function, makes it makes a reflection over x-axis. So now, if you go back, you see the purple was on the bottom, orange was on top. Purple was on the bottom, orange was on top, and here it reversed because we reflected everything. The last step is to multiply it by 1/2, and multiplying by 1/2 the entire rule of the function makes y's contract to 1/2 of their original value. So here y goes to 1/2 of it, here y goes to 1/2 of it. And then last, like, little bit of touch up on the last graph that you did, after all transformations are done. I would say, like, if there is a y intercept, you want to put it in, because we weren't so concerned over here. We were just trying to keep the shape of the function going on, shape of the graph going on. Here now we can pay more attention to little details, and y-intercept is a little detail. If I plug in 0 for x, I get the y-intercept, 0 and 4. And so let's go to another example. So parenting function was very useful. But what if I don't see any parenting function? For example, this one. This one doesn't, I don't see any parenting function. What are the general guidelines for this situation? First is find the zeros of the function. So how do I find the zeros of the function? I set each factor equal to 0. And that also gives me the x-intercepts of the function, of the graph. And so factor x minus 1 equal to 0 gives me x equal to 1. Oh, look at this. I put it on the table here. Factor x minus 3 equal to 0 gives me x equal to 3. Factor x plus 1 equal to 0 gives me x equal to negative 1. Put it in a nicely done table, and then find some test points. Find the end behavior and graph it. Okay, so how do I find the test points? First of all, I did a bunch of test points before the smallest value for x-intercept, and then then I found some points between each of the each of the zeros of the functions. And